Yeah, so far, so much for the first part of the Flink training. I hope everybody could manage to, yeah, write a first program that you could execute, or at least, yeah, get in touch with the API, play a little bit around. For this afternoon, we're going to continue with a little bit more advanced discussion of the dataset API. So far we've seen how you can use tuples and primitive types. We've seen how to use a map and reduce function. Max also told you about the join function. And I'm going to elaborate a little bit more on the advanced stuff of the dataset API, namely what kind of data types are supported, a little bit on how is that actually done internally, why is it done that way. Also talk about more transformations that the API offers, and some other concepts that might be helpful or handy in certain situations to implement certain tasks more in a nicer way, or in a more efficient way. Okay. Yeah, already said that. Basically, in the end, I'm also talk a little bit about the table API, which gives you like SQL-like expression, enables you to evaluate SQL-like expressions on structured data, which is quite neat. Okay, so we're going to start this talking about Flink's type system. Flink basically aims to support all of your data types. So whatever data object, whatever object you have, you should be able to actually process it in your in a Flink program. And Flink is using a custom serialization framework for that. So serialization is basically the process of turning an object into some kind of binary representation. So basically you do that whenever you send something over the network, whenever you write something to disk. Then some kind of serialization framework kicks in, takes your object and converts it into a raw sequence of bytes. And in the end, if you want to take it back, want to get your object back, you need a deserializer, which then takes the bytes and converts it into an object, right? There are quite a few serialization frameworks out there for Java. There is the awfully slow Java serialization. Then there are projects like Cryo, Google Protocol Buffers, Apache Thrift, Apache Avro. All of these are nice and good solutions, but Flink is doing cooking his own soup here. So we are having our own serialization framework, and the reason for that is that Flink wants to operate on binary data. And if you want to do that, you need to know how you convert an object into binary representation. Where is each field of the object being written to? So if you have, for example, a tuple string int, as you've seen before, and you want to do a grouping on the integer field, you want to know where in the byte sequence is this integer field represented in the bytes, so you can look it up and compare it directly on the byte level. You're not creating an object for that. You're really doing that on the binary representation. If you want to do stuff like that, you need to know the layout of the serialization. That's why Flink has its own serialization framework. You cannot just do that if you want to do that. Actually, you need to know, if you have your own serialization framework, you kind of need to know what kind of objects are passing through this framework. What kind of objects do I need to serialize? What do I need to deserialize? And what do I want to do with it? This is why Flink basically, in this pre-flight phase that Max was talking about, looks at your program and extracts the data types that your program uses. So if you have a map function, for example, which receives a tuple2 string int and emits another data type, say my nice POJO, then Flink internally looks at this function, sees, okay, there comes a tuple string int in there, so I know how to serialize that because I know how to serialize tuples, I know how to serialize an int and a string, and then there is another data type coming out, which is like my nice POJO, and either I can analyze this POJO, or it basically looks like a black box to me, but even a black box I could can somehow serialize, right? So there is some code when you submit your program. There's code going on, looking at your program, finding and extracting the data types that your program uses. For these data types, Flink then can create efficient serializers and deserializers, and also comparators to that can even work on binary representation in some cases. So if the data types fit, you can compare on the binary representation. All right. So yeah, I already said that basically. You have, when the program is submitted, you do the type extraction. You also validate the types. For example, if you join on two keys, you want to make sure that these keys are actually equivalent. So I cannot join on an int or the string field. The keys should match. So the system also takes care of that, obviously. And then before the program is submitted, we are generating serializers and comparators. For example, if you have these two data sets here, like a tuple 3 integer long string, the system will generate or extract some kind of type information from that. So we have here a tuple type, which is type to tuple 3, and this tuple type would then be have 3 member types: basic type integer, basic type long, and basic type string. And the second data type is a second data set is a tuple 2 with a type called person. This is like a POJO, an object that you could have defined yourself, and an integer. And the type information for that looks like I have a tuple type of a tuple 2. Then I have a POJO type of type person. This POJO type internally has again some member types, a basic type integer, for example, for a person ID, and another basic type, which is of a type string, which could be the name of the person. The data set is the programming abstraction that you're using when you write a Flink program, right? When you say when you read data from a CSV file, you say data set of this type and so on, and the tuple type is basically encapsulates what kind of data types are used in the program. A type information can be used to create a serializer for this type or a comparator for this type. So this is a completely internal structure. So you won't face it, but internally it's good to know what's happening under the hood.
So do you actually update the jar and change those types, or do you do it before the running, or do you do it on runtime?
We don't change the code. Okay. So what's happening? We basically look at the classes that are being used for sending between operators, the types that are used in your Flink program, right? And since this is a distributed system where you need to send data from one machine to another machine, these objects somehow need to be serialized, right? And deserialized. And what we do is we analyze the types and then create custom serializers and deserializers for that. So the types are not touched, but the way how the types are converted into bytes and back. More questions? Okay, so what kind of data types are supported by Flink? I said we basically want to add support for everything. Flink basically distinguishes two kinds of types, which are atomic types, which are atomic and cannot be split up, and composite types, which are composed of multiple other types. That could be other composite types or atomic types, so you can nest that, as in the example before where we had the tuple type and a nested POJO type, and so on. Basic types, so the atomic types are, we have our basic types, which are like Java primitives, int, long, string, boolean, and so on. We have array types for either the primitive arrays or also arbitrary objects. We support writable types, so whoever has implemented a Hadoop program knows, Hadoop uses all data types must implement the writable interface. So these types are also supported by Flink. So you can you can use the data types that you implemented for Hadoop. And we have this generic type, which is basically everything else which you can't fit into one of these other categories, which this is like the fall through category, everything that we cannot, where we can put a better name for it or put a better type for it, will end up being a generic type. In composite types, we have these tuple types that you've seen before. The Java API offers tuple 1 to tuple 25. We have this POJO type. What the requirements are for a POJO type, I will talk about that later. So you can write your plain old Java object somehow, which is kind of like a holder for data, and use also that as a natively supported type in Flink. And there is case class types, which everybody who used the Scala example already got in touch with. So case classes, Scala case classes, Scala tuples are a special case of case classes. So all case classes are also supported by the engine. Talking a little bit about the atomic types. The atomic types differ in a few ways. So, for example, if you have a basic type, or well, the differentiating stuff is whether you can use such a type as a key. So, if you have like this example of the tuple 2 person int, and then the question is, can you use, for example, the person as a key type? If you want to group on person, what's the requirement that you can group on this person? So, not all data types are supported as key types. The serializer is basically category is what kind of serializer is used to convert this data type, and the support for binary operation is basically important if you look at efficiency. So certain data types we can Flink is able to compare in binary form, so we don't need to deserialize the data. For the basic types, they're all supported as keys, so all Java primitives can be used as keys. It says Java Flink native, which means we just write out the byte sequence. For an integer, we just write out the 4 bytes. For long, we write out the 8 bytes. A string is like encoded with a length, and then the individual characters, and so on. On basic types, you can operate. You can Flink does binary operations, which means when you group on an integer field, this will be quite fast because we don't need to deserialize the object when we do the comparisons for sorting. For array data types, array types cannot be used as keys. They're also natively serialized, similar to a string. So we serialize the length of the array and then the individual types. And you cannot do the binary operations on it. For writable types, these can be used if they implement the comparable interface. So it's kind of like similar as in Hadoop. The key data type, whatever you use as a key in a MapReduce program, in a Hadoop MapReduce program, needs to implement the writable comparable interface. For serialization of writable types, we just hand over to the serialization methods of the data type itself. So if you have a writable type, you also need to specify a write method and a read fields method, which basically do the serialization. We just use this code then. In generic types, which are like the most generic type of objects, they can be used as a key if they implement the comparable interface. We serialize them either with cryo or avro, so you can. I think there's a configuration option for that, whether you want to use cryo or avro. And since generic types are kind of like a black box to us, you cannot do any binary operations on this. So you can still use it as key. So which means when we serialize the data into memory, we can do that. We do that with cryo or avro. But if you want to compare two objects, you first need to get the object back, deserialize it, and can compare the objects. You cannot do the comparison on the binary data.
So actually, is the best practice, it sounds like you would using always the tuples with primitives, right?
Actually, yeah, that's the most efficient way to do it. POJOs are also quite efficient. Basically, everything where Flink can knows the type. The case class actually handled the same way as tuples. So tuples and case class are kind of like equivalent. So that's the most efficient way. That's the most efficient code that you can write with Flink. So what makes an arbitrary Java object be handleable as a POJO object in Flink? Those are kind of like the general POJO rules. So you need to have a default constructor, so no arguments given. So we need to somehow be able to obtain an instance of this object for deserialization. The other condition is that all fields must be accessible. So either the fields are declared as public, or you have getters and setters which follow the common naming conventions. Say set my variable or get my variable. If you find out that your data type is not being considered being a POJO by Flink, you can turn a login, and then the type analyzer will tell you what went wrong with it. So if you have, for example, a class, this person class, if the ID field and the name field are both declared public, Flink will detect it as a POJO, as we had in the example before, and by reflection, basically find out that there is an int field and that there is a string field, and then use the int and string serializers to serialize the data. So it won't go through like a generic serialization framework like Cryo, but instead serialize the member variables, each of the member fields of the POJO by itself using custom serializers, which then also allow us doing binary operations on these fields, right? So this is an example for that. If we have, for example, a tuple 3 data type here, tuple 3 integer double person, then this would be serialized by Flink by first serializing the integer field of the tuple, then serializing the double field of the tuple. Then we would serialize the person field, which itself would then use custom serializers for the int field on the string field. So this is kind of like the byte sequence that's going to be produced by Flink. And as you see, Flink knows exactly at which position this int field will be in the byte sequence, so we can do efficient comparisons on the binary data here. So this is kind of like the why we do all this type extraction and serialization stuff, and how we can actually use even custom types natively. So why is that important? One thing is, sometimes things go wrong, or the type extractor gives you a weird error message. So it's kind of like good to know what's the purpose of having all this extraction going on. There are certain cases where the type extraction does not work so well, so you can also hint in certain cases need to hint the Flink program a little bit and help it with the types. It can make a big difference if you're using, for example, if your custom object follows the POJO conventions, so we can look into it and handle it as a POJO, or if it doesn't follow the POJO conventions, then we will use it as a generic type, which means we're going to use Cryo to serialize it. We're not able to look into it. We're not able to operate on the binary data itself. Certain things are also much easier to do if you try to use like POJO types and tuple types. I'll show a few examples of how to specify keys. So there are very nice ways of kind of like specify. For example, if you have a POJO and you want to group on a certain field, how you can actually address this field. And last but not least, all this type system is extensible. So you can provide your custom type, provide custom serializers, and also provide comparators that operate in binary data. This is not I would say, not entrance level, but rather advanced stuff. But if you're come to a point where efficiency is really important, then you might, and you have a kind of like a special data type that you want to support, or want to support in a native fashion, you can extend this type system, implement your own types, your own serializers, your own comparators that then also will be picked up by Flink and also work on the binary data. All right. Any questions about that? Everybody is Suppenkoma.
There is a simple comparison of two generic types. It's done in the binary format as well.
No, in generic types we cannot compare binary, right? So we serialize those types using cryo.
Okay,
So we don't know the byte sequence. We don't know what is where, how it is serialized. So if you want to use a generic type as a key, it needs to be comparable. And whenever we have serialized these two, let's say we just serialized two objects into a memory segment, when you compare those on a certain field, we need to deserialize the objects and invoke the compare method because they need to implement comparable on the objects and compare them, which is definitely less efficient than if you know there's a certain int field, they can just compare the bits.
Is there a way to tell the API that I'm serializing in such a way this generic object that we can say?
I mean, you as a person usually you don't have you don't have control over the cryo serializer, right? So the proper way to do that would.
If I were to plug another serializer.
Okay. Yes, I mean that's exactly what's meant by this last point. Extensible for custom data types. So you can implement your own data types, implement your own serializers, your own comparators, and so on. So you can extend the system, give it a custom type, and then it's kind of handled like a native type in Flink. But yeah, as I said, this is not this is not the thing I would start with. But it's possible, yeah. Okay. So we've already kind of like seen in the examples that Max showed you in the example in the exercise that you worked on, how you can specify like keys on tuple data types. Keys are not only used for grouping for grouping data sets. You can also use them to sort or join data sets. Whenever grouping, sorting, and joining is basically something that Flink does for you, right? So you don't need to implement that by yourself. But in order to be able to sort data or to join data, you kind of like need to specify what are the fields that I want to join on. These are exactly these key fields. So this is more generic than what, for example, MapReduce allows. From basically what MapReduce requires you to do. If you're operating in MapReduce, you always need to somehow squeeze your data into this key value pair model, right? So you always need to have a key and a value. In Flink, this is not really necessary. You can basically define the key on some component of your data type. So you don't need to have it as a separate field in a tuple. You can also basically group on the field of a POJO. So if we go back to this example here, you could also, for example, group here on the ID field of the POJO. So you don't need to extract the key. You can just address the key in your data. Keys can be either like partial or full. With that, I mean you don't. If you have a data set of a certain type, you can either use the full thing as a key, or you can also use some component of this data type as a key. You also composite keys are also supported. This is kind of like what you see in this initial mail count exercise, where you had to specify the key as the key to be the month and the address field, right? This is like a composite key made of two components. So you can also like basically add arbitrary many fields or keys to such a composite key. So now I'm going to some examples, basically how to specify keys. We're doing that by referring to an example where we want to join two data sets, namely a data set countries and a data set users. and we want to join those on a key 1 and a key 2. And if you look at both types, the countries are a tuple 3 of int long string, and the users are a tuple 2 of a POJO type person, which is an integer and a string, and the second field of the tuple 2 is the integer. So if you look at that, there are several ways how we could join those two data sets. We could join here on this int field with this int field, or on this int field and the second int field. You can also join on the strings. So there, for join the data types, of course, the data types of the keys must be identical. The first way to specify keys is to use position keys. This is basically what you've done before. You just specify here the position in the tuple, indexed by 0. So you say here where field 0 equal to field 1, which then would boil down to having here the first integer field of the tuple 3 being joined against the second integer field of the tuple 2. Yeah, this is pretty straightforward. Another thing that you can do is you can also use something like expressions. For tuple fields, these are like where you basically refer to the name of the field within the object. For tuples, this is like f0 and f1, which then gives you the same thing. These expressions have the nice property that you can also nest them. So if you now want to, for example, join the string field of this tuple 3 against the string field of the POJO, you simply say, here I want to join the third field of this tuple 3 data set, against the nested name field of the first element. Then you simply say f0.name, and name there is the member variable within this POJO. So you can basically navigate through your data types and yeah, use also nested information as a key. Yeah, you can do composite keys as you've done before, like 0, 2 here, join against f1 and f2 name. So you can basically expand that. The system will analyze that this 0 refers to the integer, the 2 refers to the string. Same here, f1 refers to this integer down here, and f1 name refers to the string. And we'll find out, okay, those are compatible types. I can join on that. Let's go for it. If you're using, if you want to join on a generic type or somehow construct a key that you want to join on, you can also use a so-called key selector function, which basically is similar to a mapper. So you get the data type in, where you want to extract a key from, and then you can generate some kind of key in some way from it. So here, this is basically just a function interface where you say, new key selector, I want to extract a key integer from this tuple 2 person int. Have to implement a getKey method, and here I simply return the second field of the input tuple. So I could have done that much easier, but just saying 1 here. But you can also you can use it for much more complex stuff. So if you want to have complex key that you want to generate, you can use a key selector for that.
Is this using binary comparison? Or is it slower than the other things where you specify the index?
It kind of like depends on what kind of type you extract. So here you're extracting an integer. What internally happens is this is going to be converted into a map function, which is done before the map, before the join, and the map function will create a tuple 2 with the extracted int as the first field, and then the original data object. So here we're going to have int and tuple. This is going to be fast. But it comes with the additional overhead of running the mapper and the additional storage overhead because you extract the type, so the integer is serialized twice in this thing, so it's not as fast as. But going to operate on the binary data. That was a question? Same question, okay, very good. Yeah, so if you're using incompatible types, the thing won't be it won't let you execute this thing. So when you try to execute it, you'll run into an exception here. If you specify the string field here and the integer field here, yeah, that just doesn't work. So it won't crash at runtime. Well, it crashes when the program is when you try to submit the program, not while the program is running. So you won't start to execute the stuff. It will crash before we go to the cluster and start a two-day job, so to say. All right. Any questions about data types and keys and stuff? Okay. Yeah, now we're going to talk a little bit about yeah, advanced sources and things, whatever that means. Yeah, Flink handles has a few built-in data file systems that we can operate on, like the local file system, Hadoop file system, S3 map-R file system. We also have kind of like wrappers or interfaces that lets us support all the file systems that Hadoop supports, like NFS, Tachyon, FTP, all the very exotic stuff. So if you have files there, you can read from these interfaces. So this is basically just the file systems that we support, which kind of like give us the bytes to read, and then there are also different input formats that then can turn these bytes into some kind of data that Flink can operate on. These input formats are kind of like in a hierarchical fashion organized. So we have this very generic file input format, which just gives you the raw sequence of bytes. So if you want to have a special, if you have kind of a special file format that you want to read, you can extend this abstract file format and implement your own custom function. Then there is a delimited input format, which is like for parses files, and you can give it a certain delimiter, which is kind of like a byte sequence where it can split the file into individual records. And then the delimited file format is an abstract format which gives you the byte sequence, access to the byte sequence of each of these separated things. Then there is a text input format which you can use out of the box. This is built upon the delimited input format and splits text files at line breaks, and will give you the strings of each. Basically, it reads the text files line-wise. So you get, if you use a text input format, you get a data set of string, and each string will be a line in a text file. The CSV input format that you already used, so you can CSV is probably not the appropriate term. We started with CSV, but it evolved into something a little bit richer. You can specify arbitrary field delimiters and also record delimiters, as we did for this mail example. There are also formats for reading binary data, and Avro input format, which reads Avro objects which were serialized using Avro. We have the JDBC input format. I know that was an output question, but you can also read data from a JDBC database. Disclaimer: it only works with a parallelism of 1, so we're not as smart. We're not so smart that we can split up a SQL query into smaller chunks. So if you can do that by yourself, but if you use that out of the box, it will only run single-threaded on a single machine. And we have wrappers for Hadoop input format. So whatever the Flink interface for input format is slightly different from what Hadoop provides, but it's still close enough such that we can provide a wrapper. So we can, if you have a Hadoop input format, you can put it into the wrapper and then also execute it on Flink. this gives us support for all Hadoop input and output formats. So, and probably most of the data sources that are out there have been touched by Hadoop, I would guess. So we can read from MongoDB with that, Parquet, ORC, Kafka, and so on. So if you have a Hadoop input format, you can just plug it in and use it. How does it look in code? So some of that you have already seen. So we've seen this read CSV file command here, which is called on the execution environment. Read text file is very similar. Read Hadoop file basically is a shortcut. We can say read Hadoop file, and then you put your Hadoop file input format into there, and that will then put it automatically into the wrapper. Same goes here for create Hadoop input, which doesn't go against files in a file system, but just is a little bit more generic. So this is for Hadoop input formats that go against files. This is for generic Hadoop input formats. And finally, the most generic way to create a data source in Flink is to call create input, and then you have to specify your the input format that you want to use. So these are basically all wrappers that wrap around this call here, making it a little bit easier. Okay. So then,
what's the reason for supporting the mapper file system?
MapR?
Yeah, mapper.
I mean, it's just an.
But we're not doing it. It's just because we're using the Hadoop file system class and they support it. We don't have any special supporting thing for mapper.
Are you sure? I think it was
File
at
system
some
is
point.
quite different than the other.
Yeah, but they have a Hadoop.
If I do, I think our MapR file system isn't that interface compatible with HDFS?
Yeah, but it's different. It's supposed to be like more efficient.
Yeah, right. I mean, it's kind of like answers also kind of like the question: why are we doing that? People are using it, so. Yeah, I mean, I think we had one of the committers had in his own cluster, or the cluster of his employer, they had MapR set up, so he added it. Not so much familiar with the details, but yeah, it was added at some point.
So if you have a gzipped table in Hadoop and then you run Flink, is it going to open one connection per one node in the Hadoop and then download them in parallel, or process them in parallel, or you know, something?
You have gzipped files.
Yeah, you have a table which is consists of I don't know 100 gzipped files, right? Like a normal hash table, right?
Okay.
And then you use your Hadoop connector for gzip files.
Yes.
And then you process the whole table.
It will work.
Would it actually like connect to all nodes simultaneously and start downloading it from them simultaneously and process in parallel, or?
I think so. So what we basically do, we basically wrap the get input split method of the Hadoop file systems of the Hadoop input format. If that gives us multiple input splits, where you would use these input splits to basically wrap them in our own input splits, and then start multiple tasks and hand out these input splits around. So one difference to Hadoop is Flink doesn't process each input split in an individual task, but instead we bring up a number of tasks and then assign input splits to these tasks. So one of these tasks might process multiple input splits. So that's kind of like a small difference compared to Hadoop, but conceptually it's kind of like close. And the input split assignment is also aims for local reads. Okay, so in the dataset basic presentation, Max already talked about the map, the flat map operator, group by, GroupReduce, and join. And in the advanced slides, we'll talk about a few more of these transformations. Talking about the reduce function, which is a bit different from the GroupReduce. Talking about CoGroups, how to specify a combine function, how to use group sorting, or reduce and union. This is not a complete list. There are more transformations out there, like more special case stuff, like for if you want to explicitly partition your data, if you want to sort a partition. We have like something like a first function where you can only read the first n elements of a data set and so on. But these are like more like the special case stuff. These are the more generic functions. Yeah, so the GroupReduce that Max already presented you is kind of like the reduce function in Hadoop, right? So you have an iterator which goes over the elements in a group, and then you have an output collector which can just takes as many records, as many elements as you give into this output collector. So you can go from n input elements to m output elements. Flink is doing that. These kinds of reduce functions are implemented internally in Flink by streaming the iterator in. So we're not materializing the full group in memory before we hand them to the user function, but instead the operators are basically streamed to this iterator. Whenever you call next on the iterator, this element is basically read from the stream, and the stream might come from disk. So if we have a large sort which went to disk, you read the data from disk. So the size of the group is not limited by the size of your JVM, but instead more or less by the size of your hard disk. So there is no need to we don't materialize the full group in memory before it is given to the reduce function. So that's also an important thing to know. And another thing, in the GroupReduce function, the input type and the output type might be different, right? You probably already used that. So you can have a reduce function which takes just takes a data set of strings and converts it into a data set of string ints, for example. Flink offers another type of reduce, which is more like the functional programming style of reduce, similar to a fault. This interface is a bit less generic compared to the GroupReduce. Less generic in the meaning that the function that you implement must be commutative and associative, and that the input type must be identical to the output type. So you cannot change the type in between this thing. However, of course, this method has not only limitations, it also has some advantages, some benefits. This kind of functions are always combinable if you implement a reduce function in this way, and the system can also execute it in a more efficient way. Right now we're not doing that, but in the future we'll also be able to execute reduce function that implemented in this way using hash strategies instead of sort strategies. So we don't need to sort the data before grouping. You can also just like think of it as updating a hash table. So how does this interface look like? Instead of like having a Hadoop reduce interface, which has an iterator over all data and a collector where you write your data in, this reduce function is called multiple types for each group, and it's called always with two elements: the first element and the second element, and it returns exactly the type of its input type. So if you think of it, if you have here a tuple 2 of longs, where you want to sum up the second field, you have a tuple 2 long value 1, tuple 2 long value 2, and then you basically add to the second long field of the first value the second field of the second value. You simply sum it up and return that value. So this is kind of like if you're familiar with functional programming, this is like combining the elements kind of like pairwise. So you call this, the system internally calls this reduce function with the first value and the second value. Then you get a result value, and with this result, and then this method is called with this result value and the next value. The result is again then combined with the fourth value and so on. So you pairwise constructing your results. This is also kind of like restriction here why it needs to be commutative and associative, and also the reason why it can also automatically be used as a combiner.
You said in Scala the tuples are immutable. How would it work there?
You create a new tuple and just emit the new tuple. Okay. Further questions to this function?
You can also do copy on tuples.
You can also copy the tuple.
Just copying it.
Yeah. Yeah. By the way, also this the input of this reduce is also streamed from disk if necessary. So we don't materialize the data here. Yeah. Another thing or another transformation that Flink offers is the CoGroup, which is kind of like which is a binary operation on two inputs, similar to the join. What it does, it basically groups both inputs on a certain key. So you build groups on you group both input data sets on a key. You build groups there, and then it gives all groups that have the same key of both inputs together to a CoGroup method. The CoGroup method has two iterators for both groups, and then output collector, which then takes whatever you want to write out. So in a sense, this is similar to a GroupReduce function with two inputs. So you can see basically here, if you have this is one input data set, this is another data set. The colored field is like marks the key that we're operating on. Here we have the blue keys. So this data set has two blue elements which go into one group here, and the second data set has one element with a blue key which goes into this group here, and then all of these records are like processed together in by the CoGroup function. If you have, for example, this yellow key here, so there's only one element with a yellow key in this data set and none in this data set. This will also yield a call of the GroupReduce function, where we have one iterator with one element here and an empty operator for the other thing. So compared to the join function, if you compare to the join function, this call would not have happened, right? Because if the join is doing an equi-join, if there's no matching join partner, there's no function call. So basically, it's kind of like filtered out in join. Whereas in CoGroup, you have an iterator over the one side and an empty iterator over the side, which didn't have an element with a matching join key. Yeah, what you can do with the CoGroup. So the Flink join is an inner join. What you can do within CoGroup, you can, for example, emulate an outer join, because you're gonna find out when one iterator is empty and then like fill up the other fields with null values, for example. Or you can do something like an anti-join, which is done in this example here. So we have one data set, tuple2 long string here, and another data set long here. And the goal of this operation here would be to only let elements of this data set D1 pass if there is no entry for data in data set D2. So we use here. Oh, sorry, there's actually an error. There's a mistake here. So we use here the long field of the tuple2 as a key, and here we would use the long value of D2. So this needs to be this would work here, but okay, you need to specify the key a bit differently here. And then we call the CoGrouper here, which is then implementing this interface, CoGroup tuple2 long string for the first input, long for the second input, and the result is the string, and the result data type would be string. And you see in the interface here, the method is called CoGroup. We have an iterable over the tuple2 long string, this data type. We have another iterable over the long value here, and a collector for the strings. And if the iterator of the second input is empty, so if not has next, then we would collect all the string values of the other iterator. So this is kind of like an anti-join. We only let things pass if the other set is empty.
Maybe a bit more generic question. Which of these operations are costly cluster-wise in the sense of they cause then synchronization or shuffle between nodes, and which are like local and cheap in that sense?
Yeah, so maps are trivial, so those are local. Whenever you have a key operation, it's going to cost something, right? So you're going to shuffle data over the network, because you need to partition data, you need to organize data for the key. How costly it is? That kind of like depends a little bit. Flink for joins, for example, Flink implements different join strategies. So you can do the optimizer can choose to do a broadcast forward join, which is kind of like similar to an equivalent to a map side join in Hadoop, where a smaller side is replicated to all parallel nodes, and the larger side is kept local. So you don't only have to ship the small side. Or you do a repartition join, where both sides are shuffled over the network, which is similar to a reduce side join in Hadoop. Then on each local instance, once you have the data brought to the right machine, there are different strategies that we can do for joins. We have hash joins, where you can build a hash table from one input and probe it with the other side. Or we can do a sort merge join, where we sort both inputs and then compare the elements. So all of these decisions are kind of like done by the optimizer, but you can also hint the optimizer there's a way to say, I want to have this side broadcasted and the other one forwarded locally. I want to use a hash join like that. CoGroups are always executed using a sort merge join. So we always have to shuffle data over the network. We always have to sort both inputs. Similar for reduce and GroupReduce, you also need to shuffle data over the network and need to group the data. As I said before, for regular reduce function, this functional style of reduces, we might add, or we're thinking about adding a hash strategy there, so we can get around the sorting part for grouping. It's a tricky question. What is expensive? So basically all things that have a key somehow need to reorganize the data. But there's also good news. The Flink optimizer does a fairly good job in inferring when it needs to shuffle data. So there are certain situations when you, for example, have a reduce on one key and then do, for some reason, a join afterwards, which is on the same key. Then the optimizer can figure out that the data is already partitioned and it won't shuffle it over the network again. In some cases, you need to give a little bit more information to the optimizer, which is kind of, we call that function annotation. So if you have a custom function and your custom function processes the data, we don't know if you change the data, right? So we don't know if the data is still partitioned afterwards. So you can, Flink offers a way called forward annotations, where you can say, I touched these and these fields of my data, all the others are kept constant. If I partitioned on these constant fields, the data is still partitioned afterwards. So there are ways to let the system know that it doesn't need to shuffle data around if it's not necessary. All right, talking about efficiency, good point. Coming to the combiner, right? I guess who of you knows what a combiner is? Or a combined function, like in reduce, like in Hadoop? Okay. Combiners are basically used for local pre-aggregation of data. So if you want to compute a sum, for example, and I have a huge bag of huge data set of longs, and I want to sum it up, I can either bring them all to one machine and sum them up, or I can compute partial sums on each machine and just send the partial sums to one machine, right? And this is basically what a combiner does for you. It offers you a way to do a local pre-aggregation data, crunch the data down on each local instance, and then only send this already reduced data over the network. Combiners can be done basically before GroupReduce functions and CoGroup functions. So whenever you have operating on a group of data, they're useful. The functional GroupReduce injects these combiners like automatically due to this restricted interface of summing up or of combining two elements to one. This interface basically guarantees that you can use the same function also as a combiner. Combiners are usually, of course, it's arbitrary code. You can implement whatever you want in a combiner, but usually they are optional for semantics, but crucial for performance. So it can really speed up a program because you reduce the data that is going to send over the network quite a lot. Here's a small example of how that actually works. So this infamous word count example. Here we're not counting words, we're just counting letters. If we have like three parallel map tasks here, this one has should count all of these. The task here is here to count the letters. The input for the first mapper is A, B, B, A, C, A. The mapper would convert that somehow in pairs of letters and integers. So we would have A1, B1, B1, A1, C1, A1 for each of the letters here. So do all the others. And if we now apply a combiner, which then sums up the int field, you basically end up with 3 records here instead of 6, where A is 3, we get a record A3, C1, and B2, and so do all the others. So basically crunch the data down here, like in this example, only half the data set size. Then it's sent over the network to the reducers, and this reducer will take care of summing up all the A and C counts, and this is taking care of the B and D counts. So if you have now much more data, possibly a few of the words very frequently occurring, then you can see that by doing this pre-aggregation, you can reduce the amount of data that's sent over the network quite a lot and save definitely network bandwidth.
It's like the combining and reduce functions are the same, actually. It looks like the combine and the reduce functions are the same. So
Yes.
it's just that we have to specify something explicitly we want the combine step, or
in this example, that's true. This is kind of like we could also express it with a functional reduce here because we're just summing up this stuff, right? But if we have this generic group reduce interface where you just have an iterator, you can do arbitrary stuff in there. A combiner, that's a good point. A combiner is basically used by implementing a rich group reduce function, which has, compared to the regular group reduce function, additional methods, including a combine method. And this combine method here has, as you see, the same interface as the reduce function, right? And in its default implementation, it just forwards to the reduce method. But if you want to have custom code, you need to override it. And it's not used unless you annotate your user function with this annotation here, combinable. So if you implement your group reduce function, it won't have a combiner unless you add the combinable annotation. Once you add the combinable annotation, you should make sure that the combine function is properly implemented. So either you leave it at the default implementation, which forwards to the reduce implementation, or you override it and give your custom code there.
and the last sentence here means that basically Flink could do it automatically if it's so it would run this combine step on the local machine and then it is possible.
Yes. So if you have the combine method here, if you enter a group reduce function, which has this combinable function annotated, it will be injected into the data flow automatically. You don't have to do anything else. Then basically implement it and tag it with the combinable annotation. Oh, they're streamed. They're streamed to the reducer. So internally the combiner basically works. The combiner is not doing a full pre-aggregation. So that would be again very expensive. Imagine you have a lot of data coming in. If you want to do a full grouping, you again need to sort the data, right? So the combiner is doing kind of like a least effort combining thing. It has a memory, a certain amount of memory. It collects data until the memory is full, sorts the stuff in memory, applies a combine function, and then everything, the result of the combine function is forwarded. Then this memory segment is again cleared, and the next data comes into this this memory segment. So we don't do a full pre-aggregation because it would be too expensive to sort the data, going to disk, going back to writing to disk, reading from disk. Instead, we're doing like a least effort thing, sorting in memory as much as we can, and then forwarding the data. There's also a dedicated group combine function, which has the same interface. Oh, I was wrong. This slide is wrong. Sorry. So in fact, the interface of the combine function is not the same as the combine function, as the reduce function. So the input type here must be the output type. So it should be collector I. So if you have a combine function which is injected before, like transparently injected before the reduce function, the type of the data must not change, right? So this O should be an I. Yeah, sorry for that. Yeah. So the interfaces are basically very similar, but the input of the combiner must be like the output of the combiner. If you want to have a little bit more flexibility, you can also use the group combine function, which then is has the same interface as the group reduce function, and there you have this interface here. This is then not transparently injected into the data flow, but you explicitly say, I want to run this combiner, and I know what I'm doing, and put the combiner there. So this is kind of like more an explicit thing. Okay, more questions about the combiner?
Maybe again a generic question. How does this work in streaming fashion? It's like doing this.
I mean, streams are a completely different story when it comes to like grouped operations, right? So
this is all for batch.
This is all for batch, yeah.
Okay.
There's also a thing in Hadoop called like the secondary sort, which basically means that you wanna read the data into your reduce function, group reduce function in a certain order, right? So imagine you have a group of elements which you consume via the iterator, but you want to have them in some order, right? What you could do is you collect everything, sort it yourself, and then apply your function. But this is, first of all, it's kind of like bound to the, you need to collect all the data in memory on the JVM heap, which might be inefficient. You need to implement it yourself. And your user code also gets basically cluttered with all these data reorganization. This is why you can also like specify that the groups that you receive via in your GroupReduce or CoGroup function should be ordered in some way. You basically say that by calling here sort group in between. So you say a group by, which means here I group on this tuple 3 long. I group on the first field of this long tuple. Then I sort the group on the second field of the long tuple in ascending order. And then I apply my GroupReduce function, which then will receive all the, which is called for each group of field 0. And the values in each group are then ascendingly sorted on the second field of the tuple. So that makes a lot of algorithms, in some cases can make your user code first easier to read and also more efficient because you don't need to first materialize all the data in memory. And the good story is it's almost for free. Since we sort the data anyways, just adding one more field to the sort is usually not such a big deal. So we sort the data for the grouping anyways. Just adding another field for sorting the elements within a group is usually quite cheap. All right, so what happens if you forget to add the group by in front of your reduce function, group reduce function? So basically, don't say data group by group reduce, but instead just say data group reduce. Then you'll basically end up with an all reduce or all group reduce, which means that your data is not grouped. Basically, the full data set is your group, and you apply the GroupReduce function on the full data set. This has a few nasty implications, namely all data is sent to one machine, and everything will run with a parallelism of 1, right? So this can be fairly inefficient unless you use a combiner. So if you know what you're doing, you can use a combiner, do the pre-aggregations locally, reduce the data which is sent to one machine, and also, not in this case, probably not only the data that is sent over the network, but more importantly, the work that needs to be done by this one poor single thread, right? So you can do global aggregations, global reduce, but yeah, make sure you have a combiner for that. Is that clear? So if you don't specify groups, the full data set is your group and goes into one function call. Okay, so this is probably the most trivial transformation that we offer. It's the union, which basically just takes two data sets of the same type and unions them. So all elements, so the resulting data set will be all elements of both other input data sets. We don't do any duplicate elimination, so it's kind of like in SQL union all. It's just combining the streams, so to say, and all data can then be forwarded in another operator. Okay, all of the functions, or most of the functions that we handled before, were like functions which only had one single method, right? So a reduce function or a map function or a flat map function, these are interfaces with a single function. And we did that to have basically this SAM interfaces here, which are necessary to be able to specify Java 8 lambdas. So you just have one method to implement, and if you specify a Java 8 lambda, then it's pretty clear which method you're implementing, right? Because there's only one. If you want to do a little bit more fancy stuff like initialize your operator or configure your operator, you can use the rich variant of all of these functions. In addition to the operation function, like the map function in the map, or the reduce function in the reduce function, there's also like also additional methods like open, close, and something called get runtime context, which gives you a little bit, a context about the environment in which you're running. So if you want to configure your operator or want to do some startup initialization, you can implement the rich function and do that in the open call. The open call will be called just once before the first function call is happening, and the close call will be called just once after the last function was called. It's not possible to emit data in the close call. So if you the only way to get data out of your function is during a regular map call or reduce call or join call, for example. So what can I do with this runtime context? This runtime context gives you a few information like the index of the subtask. So if you have a mapper running with a parallelism with a degree of parallelism of 4, so there are 4 mappers running in your cluster or somewhere, then this index of subtasks will tell you which mapper it is. Is it mapper 1, 2, 3, or 4? The next method, get number of parallel subtasks, will tell you how many mappers are there around. So it will return 4 in that case. And then there is also like a called get execution config, which is a global config for the program where you can just set variables or configuration stuff. So you can set that at the execution environment, and the execution environment will basically take that thing and give it to your user function, and you then in the open method you can access this thing and configure your function as you like. The runtime context also gives access to the so-called accumulators and the distributed cache. Broadcast variables, right? I do have distributed cache, yeah. What these are covered now. So what are we have some additional stuff which are not like fit into this function pattern, but are some kind of like helpful to implement certain things. One of these are so-called broadcast variables. These are just regular data sets which can be broadcasted to each parallel instance of an operator. So say we have a mapper that should assign certain IDs to words. Then we have kind of like a hash map or a dictionary for the words with an ID. Then we can have a regular data set down here of strings and ints, where the strings are the keys and the ints are then the IDs that we want to map to. We can just broadcast this data set to each of the map instances, and the map can then take this broadcasted data set, convert it into a hash table, for example, in the open method, and then use this for the regular processing. So it basically looks like this. We can create a data set here. Here it's just a data set of integers, which we create by calling this from elements call. So this will create a data set of integers with 3 integers, 1, 2, and 3. And then we can take any regular map call here, and we say with broadcast set, give a reference to the data set that we want to broadcast, and then we give it some name here. And this name, the name is used to identify the broadcast set. So you could also add another broadcast set. So you can add as many broadcast sets to an operator as you like. So it's not very common, but you could add 1 or 2. And then if you're in your rich function, you can call this get runtime context method, and then say get broadcast variable, and then specify the name. And the return of this get broadcast variable call is a collection of integers in this case.
Is this mutable? So can I first add 1 to 3 and later add also 4 and 5 and then revert this?
No. So the data set. So the data set here is not mutable. So when you say this, when you call here this with broadcast set, it will exactly take the value of the broadcast set variable at that point, and that will be forward. So this is not a synchronized data structure.
So
It's
you need a rich function to use this.
you need a rich function to do that because you
In Scala API the same?
yes.
Do you have something like this, but that will be mutable, so you can change it?
Iterations.
Hmm?
When you would use iterations. Yes.
Yeah, you can. If you use something like iterations, there you can basically update the broadcast set in each iteration, so that's possible. But within just a constant flow, no, just injecting new data, that's not possible. Yeah, it's also like a tricky thing to do in a distributed system to get that right with all the synchronization stuff. Yes, that's exactly, that. You can read the file first in. So this is not like a distributed cache. This is more like, it's used for distribute data sets, like in the sense. So you can read the, I mean, you could if you have a file input format that just reads a binary blob. Yeah, it's maybe not the most intuitive solution, but you can use it like that. And of course, the broadcast set shouldn't be too large, right? They need to fit into your into the heap. If you're just broadcasting huge sets, this is not the intended way to do it.
You cannot
broadcast arbitrary objects, not only data sets.
You can broadcast arbitrary objects, arbitrary data sets.
Data sets. Only data sets.
Only data sets, yeah.
Oh. Not only serializable.
No. For this broadcast set, it needs to be a data set, yes. I mean,
Trying to change it to something. Just anything serializable, I imagine.
Not sure. I mean, you can. I mean, you can use a data. You can build a data set with a single element, of course. If that's that will then be like if it's serializable, it will be shipped. Yeah. Yeah, maybe it's a way. Maybe we can make a shortcut for that actually. More questions? Okay, then I think this is kind of like the last thing of the API that we cover here is our accumulators. These are kind of like similar to counters in Hadoop. So this is a very lightweight way to compute statistics on your data. So if you want to like count how many records your functions are processing, you can use, for example, an int counter, a long counter, which is just increment whenever you see a record. You can also compute histograms, so it's a little bit more generic than the Hadoop counters. So you can implement your custom accumulators, which are like built up locally. Then they have kind of like a merge function that you need to implement, which allows to combine multiple counters, and these are then kind of like combined and sent to the master node. So this is not meant to hold a lot of data, but can be quite handy if you need to verify certain assumptions about your data. Just count how many records are being processed. Maybe see if your data has a significant skew. If you want to have histograms, if there are certain keys, certain elements occur very often in your data set. So then these accumulators are a neat thing to use. It works basically like this. So you have, for example, if you just count how many words are in your text corpus, in the map function, you just increment the counter by 1 whenever the method is invoked, and then at the end, these counters are like sent to the job manager, which is the master working node, which then again, as I said, needs to have some kind of a merge function to combine multiple of these accumulators, and then the final result. You can see the final result. You can use them again using the runtime context. To use the built-in counter, you just say get runtime context, get long counter. Again, you can you specify a name here. The name here needs to be global in your program, not only global in your function, but global over the whole program that you're executing. And then you can say add 1 or add whatever. You can also not only count how many records you have, you could also like add up the size of each element. So if you have certain like string length, you could always add the length of the string. So there's not simply counting. You could basically, in this case, add anything to this counter, and then in the end, the counters will be collected after the functions. After the function finishes, and the final result will be made available. And you can get the result of these accumulators either by the job execution result, which is actually returned when you say environment execute. The environment also has, if you're using print, for example, there is no execute call, then you can fetch this job execution result from the execution environment. The execution environment also has a method which says get last job execution result. So this will then give you the last result. And then you can just, on the result, you just say get accumulator result and give the name of the accumulator that you want to have. The accumulator is also displayed by the command line client if you execute a program, or in the job manager frontend. So, okay, so much for the dataset API. Are there any questions? Wait. Oh my God. Sorry, guys. We already talked a little bit about this table API, which allows to do like this SQL-like expression data. And yeah, here are just a few slides basically give a feeling what it is, how we can use it. Yeah, it basically makes the analysis of structured data really easy. Structured in the sense that you have like a relational schema, flat relational schema, and yeah. So for a lot of this, with Flink or with the dataset API, it's a very, very generic way of processing data, right? So you can write a map function, you can write a filter function, a join function, but all of that goes into like your custom code, so you can do whatever you want in there. Whereas if you want to just do some standard default operations like a relational join or a sum aggregation and average aggregation, you can do that with this generic framework, but it's kind of like painful because, you know, in SQL I would just write, I don't know, sum, and it would sum of the things, and here I need to implement a whole Java class just to do the same stuff, right? Since the framework itself is so generic, you can actually like execute all the stuff like SQL on top of it. However, you need to have some kind of translation between that, and this is kind of what the table API provides you. So it gives you a lightweight way of execution of processing relational data with concepts that you are probably all familiar with, like SQL. The table API is tightly connected, integrated with the dataset API, also with the data stream API, but so it's fairly easy to have a data set, like this dataset abstraction, convert it into a table, run some table expressions on this table, and then convert it back into a data set and do some further processing. So this is really fairly easy. What happens under the hood is with these SQL-like expressions, they're going to be converted into like executable code, and we do that with code generation. So this Alyosha did that. So there are some magic Scala compiler things going on there to just compile the code that is then executed. The basic data structure of the table API is, not surprisingly, a table. And table here is similar to a relational table. So you have a structured data with named fields, named columns. And whenever you evaluate an expression on this table, the result is going to be another table, possibly with another schema, but you basically go from table to table to table, similar as you go from data set to data set to data set. What kind of expressions do you have here? For example, you have here a table T, some other table called ORIC here, and you say as author title pages, which then will basically just be a renaming of the fields for this table. So here we have basically the first field is going to be called author, the second title, and the last one pages. Now you can do some neat stuff like filter on this table T, say T filter pages larger than 100. So this will filter out all everything where pages are smaller than 100. You can project on the table, say basically, okay, I'm not interested in the pages, I just want to have the author and the title, say select author title, or also evaluate some expressions on there, say for some reasons I want to multiply all pages by 2. You can group the table by saying table group by, then give the name of the column that you want to group on, and then say select pages dot average as average pages to basically give you the average number of pages of certain authors. And you can also join two tables by saying table join. Here's another table. Here this is kind of like a little bit nested, so I could also say table 2, which is some arbitrary kind of table. Here just say table 2, where the author equals author 2, and it shouldn't be select, should be as, and then you can basically build your result tuple again using the select statement. So these are kind of like the expressions which are currently supported. So you can do like easily filter data, you can easily project data, join it, and aggregate it. The table API will also be extended with more SQL-like expression functions like string functions and so on. I think right now we have support for a substring there, but this is going to be extended. So whenever you, I mean, SQL support is really like it's like open-ended. The box of whenever you start doing that, you open the box of Pandora, but the feature set is going to be extended in the future. So how do you get to a table? So assuming we have a Java data set or a data set in the Java API, we basically need to instantiate a so-called table environment to do the conversion to table and back. So assuming we have a data set table 3 string long double, then you can create a table environment by just simply say new table environment. Then you can create a table T here down by saying table environment to table data set, and then as name count price. So you have to give names to the field, to names to the fields of the table. Coming back from a table to a data set. This can be done basically in 2 ways. You can convert it into a custom POJO data set, where the POJO fields must map the table names of the table fields. So, for example, if we have here an example where we have a Java POJO called stock with 3 fields: the string field called name, the next field count is an integer field named count, and then double, which is price, and you have a table which has exactly the same names. Then you can simply say table environment to set. You give the table there and the class of the POJO into which you want to convert it, and you then get a data set stock or of type stock out of that. If you don't want to implement your own POJO, you can also return it as a row, which is a very, very generic thing, but it's not very easy to work with. If you just want to print out the data, converting it into a data set of rows is good enough. All right.
That's it.